table and model the periodic table trends. Consider the properties given to an element and make locates in your element on the periodic table. Justify one thing with evidence of each of the models provided. Describe the pattern of trends of each model and how the associated property from the element relates to that trend, thus providing evidence for the location of the element. Property removed discovered element in the mass number is 3 or 4 and very low ionization energy, bonds easy with other elements. Melting point 50.1 Celsius, the smallest electronegativity. Predicted the largest atomic radius, great metallic character, and silver color.
Okay, so we have a new element has been discovered, and we have some properties here. All right, so the first property they're looking at is the low ionization energy. So I'm going to show you some trends on the periodic table. The first trend that they're looking at, this is what you should have done. You should have examined some trends. So ionization energy. I'm just here for the food. All right, so this is the trend for ionization energy. And you'll notice that ionization energy increases to the direction of the nonmetals. Fluorine would be a nonmetal. You see the arrows?
What is it then?
Going up to helium and going to helium in both directions. So we have low energy here and we have high energy there. So what does the sheet says? Very low ionization energy. So does everybody see how that fits right here?
So,
Yes.
so it goes like kind of like this. And then like, it's one just right out.
Right, so the next thing would be melting point or bonding. So we're going to take a look at melting point trends. This is color. We'll just go to color next because I got it on here. The last one is color. It says silver in color, so you can see the silver in color there. Lithium, sodium, and potassium. That would be the alkali group. Here's electronegativity. That's number 3. And you'll notice that electronegativity increases in the direction of fluorine. So fluorine has the highest. It has a scale of 4. Right? This is low, medium, high. Cesium, which would be a little bit above francium. Francium has the lowest. So you can see here low. This one's higher. So this is the lowest. This area would be the lowest electronegativity. And then we have atomic radius. You can see that the radius is increasing going from the nonmetals to the metals. So these have a higher atomic radius in this direction as well. This diagram really shows you metallic characteristic. So number 5, metallic character trends. The metallic character tends to increase as you go towards francium from the nonmetals over here. And the melting point, let's see here. Here's the atomic radius again. We have cesium the largest. That's kind of a better model to look at. You can see how this one here is the largest. So if it has the largest atomic radius, it's going to be in this location right here. Does everybody see that? Make sense? Remember, this is as an element, not an ion. These atomic radii are shown as elements, not ions. All right, so let me search melting point trends real quick. We'll put that up there.
Yeah. Isn't that orange? That's red.
See it?
Yeah.
Do you see these lines here?
Yeah, but they're all purple.
And become excited. These excited atoms return to their stable state by emitting light to release that energy.
Locates the new element on the periodic table.
Very good. Yeah, come on up here. Do we get points, Mr. Kirk?
Well, you get to see something you're not going to see every day.
I think it's bright. It is very bright.
Well, the lines are associated with the electrons moving to the second energy level. The dominant one is the one you're going to probably see the most of. That would be, because the lighter ones are going to be more difficult to see. They could be hidden in there. And that's why you have to have this, I guess you would say, prism. There's a prism inside of this spectroscope that's allowing the lines to be divided like this. Because when we turn it on, you're not going to see this. Is everybody clear? This is what you're supposed to see when you look through the spectroscope. So what color do you think the neon's going to be? Yellow? Raise your hand for yellow. Okay, raise your hand for blue. Raise your hand for green. Now it's red. Now this color is the dominant color to use like at nighttime for lighting. Why do people prefer to see red lights at night? It's easier on the eye. Like your brake light when you're driving down the interstate is easy on your eye compared to like somebody coming to you with their high beams on. You're kind of like, yeah. So high beams are not good. TCT. And the first one up here is ionization. Now you'll notice that the ionization is low where you see francium, the metal at the bottom of the periodic table there. It's in the alkali group. So this is francium right here, alkali group, low energy. That's low ionization energy. So if you look at your TCT, it says very low ionization energy. So that would be a bullet point you might write on your paper. It has very low ionization energy. The next issue there concerns melting point. We'll get to that. We're showing electronegativity here, and it shows you that at francium's alkali group, you have a low electronegativity. It says low right there. Does everybody see that? This up here in red is high. Fluorine would be the highest. Electronegativity is what? It's a measure of the atom's desire for an electron. Nonmetals tend to have a great desire for an electron. Metals tend to want to give them away. So the analogy could be, metal is like a man. It wants to lose its energy, and a woman is like a non-metal and wants to gain. So there are different degrees in this strength too. Fluorine would be the most aggressive, and like francium would be the most aggressive. So keep that in mind that electronegativity is very powerful. When you look at chlorine, when you throw it on, let's say, a shirt, it's going to take those electrons. It's very aggressive. If you drop sodium in water, it explodes. So if you have a temperament like that, you need to be very careful about the decisions that you make, because you don't want to go explosive on somebody, because that could get you in trouble with the police, like over at J-Town yesterday. Alright, so electronegativity. And then we have melting point. We'll come back to melting point. We did it last. The color of the metals, we have like silver. They said the color was silver. And in this group, lithium, sodium, potassium, you can see that those are silver. That's another indicator you could write down. Metallic characteristic. That's another bullet point number 5 over here. So the metallic characteristic tends to increase as you go towards francium. So it says right here increases. That's increases right there. As you're going this way, and it decreases that way. Obviously metallic would be metal. Now atomic radii, this is going to be for the elements, not as an ion. So you'll notice here which atomic radii is the largest. Raise your hand. Points. TT. Right, francium. So this group here, it goes cesium is large, and francium is going to be the largest. So it most likely might fit in the alkali group. Now the last thing we want to look at, the last really, really good evidence, is going to be the melting point. So if we blow this up for you, you can see that the circle means unknown. This is telling you that they do not know the melting point. So these are unknown. And right here, this is from 0 to 200 degrees Celsius. 0 to 200, and then it jumps to 200 to 800. So this group right here is going to be associated from 0 to 200. So what's the melting point of the unknown new element?
50.
It's around 51. Very good, Gabby. So, Gabriel. So it's going to fit most likely right here. You can see how it's higher right here. Everybody see that? Any question there? It's higher there. And it goes to lower here. All right, so make a note of that. I'm going to come around now and check. We're going to examine the spectra of nitrogen. That would be the element spectroscopy of nitrogen. This is what it should look like. So we're going to turn this on. What color do you expect nitrogen to be? Anybody know? Blue. Let's take a look. So it's purple.
Predicatively the largest atomic radius, great metallic character, silver color.
Okay, so I'm going to collect this sheet called the Chemistry New Element TCT. This is a thorough course task. So every school is doing this, like Moore High School, Manual, they're all doing these TCT tasks. Now if you look, it has some things that it wants. It wants to know the properties of the new element. You're going to identify it in which group and period. And it's talking about ionization energy, melting point trends, electronegativity, and so forth.
Strontium nitrate solution and then inserted into a burner flame. The strontium atoms with their characteristics of color. Perform a series of flame tests by doing many labs.
Right, the melting point on the data sheet says around 50.1. This color right here corresponds to 0 to 200. So if you notice, the melting point is kind of decreasing. This is a darker color, and it's decreasing as it goes down this alkali group. Now this alkaline is much higher, the melting point is, and it's much higher over here. So you can notice it's going higher over here, so the melting point alone is going to push it into this group. So check yourself.
Although it contains only one electron, Bohr's idea is illustrated in figure 5.2.
Okay, so yesterday we learned about when atoms emit energy. Like we learned about them emitting colors, right? And we also learned about atoms absorbing energy with this particular assessment. So what we just read states that when atoms absorb energy, what state do they get into? Raise your hand. What state is an atom in when it absorbs energy? Raise your hand. The excited state. Very good. It's very important to remember. That's why this table is a good visual to keep in mind.
The new element has been created in a large hadron collider that concerns atoms. And you're on task force to determine whether this new element should be placed in periodic table. The International Union of Pure and Applied Chemistry was deciding after validating evidence for its existence. Using the provided models of the periodic table and model the periodic table trends, consider the properties given to the element and make a showcase in your element on the periodic table. Justify one thing with evidence of each of the models provided.
Let's listening then.
Describe the
Shame
pattern
time.
of trends of each model and how the associated property of the element relates to that trend, thus providing evidence for the location of the element. The property of the newly discovered element and the mass number is 3 or 4 mu, very low ionization energy, bonds easy with other elements, melting point 50.1 Celsius, the smallest electronegativity, predictably the largest atom, atomic radius, great metallic character, and silver color.
Okay, so we have a new element has been discovered, and we have some properties here. All right, so the first property they're looking at is the low ionization energy. So I'm going to show you some trends on the periodic table. The first trend that they're looking at, this is what you should have done. You should have examined some trends.
So ionization energy. I'm just here for food.
Really isn't okay.
All right, so this is the trend for ionization energy. And you'll notice that ionization energy increases to the direction of the nonmetals. Fluorine would be a nonmetal. You see the arrows
What is it then?
going up to helium and going to helium in both directions. So we have low energy here and we have high energy there. So what does the sheet says? Very low ionization energy. So does everybody see how that fits right here?
So,
Yes.
so it goes like kind of like this, and then like, oh, it's going this way to that way.
Right, so the next thing would be melting point or bonding. So we're going to take a look at melting point trends. This is color. We'll just go to color next because I got it on here. The last one is color. It says silver in color, so you can see the silver in color there. Lithium, sodium, and potassium. That would be the alkali group. Here's electronegativity. That's number 3. And you'll notice that electronegativity increases in the direction of fluorine. So fluorine has the highest. It has a scale of 4. Right? This is low, medium, and high. Cesium, which would be a little bit above francium. Francium has the lowest. So you can see here low. This one's higher. So this is the lowest. This area would be the lowest electronegativity. And then we have atomic radius. You can see that the radius is increasing going from the nonmetals to the metals. So these have a higher atomic radius in this direction as well. This diagram really shows you metallic characteristic. So number 5, metallic character trends. The metallic character tends to increase as you go towards francium from the nonmetals over here. And the melting point, let's see here. Here's the atomic radius again. We have cesium with the largest. That's kind of a better model to look at. You can see how this one here is the largest. So if it has the largest atomic radius, it's going to be in this location right here. Does everybody see that? Make sense? Remember, this is as an element, not an ion. These atomic radii are shown as elements, not ions. All right, so let me search melting point trends real quick. We'll put that up there. Is the important concept to remember. So if you have, let's say, an orbital, or you have 1, the first orbital, you put that there and you get 2 electrons, and then you put 2 into this equation, you get 8 electrons, and then 3, 18. So how many electrons can the 5th orbit hold? 50. Is that clear? Claire? The 5th orbital can hold 50 electrons. Now, will it have 50 electrons in it? No. Not typically. What happens, you have something associated with the charge, and 50 electrons are a lot. So what will happen, you'll go into the valence shell, which is the outermost shell, and then you tend to have 8 electrons. The atom likes to have 8 as far as stable is concerned. So it will build its lower levels to support the outer. We'll talk more about that later. The rules are associated with that.
Although glass can be heated.
What part should I be looking at? Should I be looking at the thing or the whole thing next to it?
To the thing to the right.
Okay.
Push the button, you can see
It lights up
the grid.
Yeah. Okay, so that's all. I've just been staring at the straight object, and I'm like, I can't see any colors.
Inserted into a burner flame. Strontium atoms emit a characteristic red color. You can form a series of flame tests by doing the mini lab.
Okay, very good.
Producing the glow. Note how the line nature of hydrogens.
minute that will not take by the laws of class.
Allowable energy state. The lowest allowable energy state of the atom is cold.
Right, that's silver there, right? Is seeking to do what in the excited state, Noah? Yeah, it's seeking to donate. Typically, the elements that have electrons in excited state would be the metals. They're the ones that are going to be donating electrons. The nonmetals, they tend not to get in super excited states just because they're diatomic. What does that mean?
They all die atomically.
No, oxygen is bound with itself, right? So you don't see O out there lonesome all alone. Like you can get one sodium atom by itself. The sodium atoms don't bond with themselves. They can be together in a group, but they're not bonded. Whereas oxygen and the other nonmetals tend to bond with themselves, like oxygen, chlorine, fluorine, O2. Now in O2, when carbon gets in the presence of O2, then it's going to form CO2. Why would oxygen leave itself and form with carbon? Close. Why would oxygen leave itself and go to carbon?
Maybe it can't help it when it's just a
Well, it's going to go after these excited electrons. When you strike a match, you're activating the energy to create an excited electron in a forest fire. And the oxygen's like, look, carbon is a better provider than oxygen is itself. Oxygen is like, look, I like being with you, but carbon's a better provider. What does that mean it's a better provider? No, it's just going to provide its electrons with less work. Exactly, less work. So oxygen is going to do less work hanging out with carbon than it's going to do hanging out with oxygen. Brightness coming through. No, you don't want to turn that. That's going to take it out of. You want to move this to where it lines up. You should see the straight line. A straight line similar to what you're seeing right here on this card. All right, let somebody else take a look at it, and I'll follow back with you.